Welcome to The Deep Dive, the show where we grab a stack of incredible sources, articles, research, our own notes, and really pull out the most important bits of knowledge and insight just for you.
That's right.
Today, we're embarking on a journey into something incredibly small, yet, well, profoundly significant. We're going to unpack something so fundamental, so ubiquitous, that it underpins absolutely everything around us. I mean, think about it. From a single shimmering drop of water to the farthest star twinkling in the night sky, it's all built from these incredibly tiny, invisible particles.
Atoms.
Atoms, exactly.
And that's our mission today, to take a truly deep dive into these fundamental building blocks of matter. We'll journey from the very first sort of ancient philosophical inklings of their existence,
Right back.
all the way through the groundbreaking scientific discoveries that revealed their true nature, right up to the cutting edge of quantum mechanics.
So you'll understand not just what atoms are made of.
Right, but the fascinating story of how we came to comprehend them, how they behave, and their surprising fundamental role in the universe's past, present, and, even its distant future.
Okay, listeners, get ready for some serious aha moments.
Definitely.
So let's just lay the groundwork first. What is an atom at its most basic level?
Okay. At its core, an atom is the basic particle of any chemical element. It's the fundamental building block of all matter.
Right.
When you picture it, try to imagine a tiny, incredibly dense nucleus right at the very center. This nucleus typically houses both positively charged particles called protons and neutral particles called neutrons.
Okay, protons and neutrons in the middle.
And then surrounding this compact nucleus, you have this dynamic swarm, almost like a cloud of negatively charged electrons.
And they're held there.
Yep, held in place by a powerful electromagnetic attraction to that positive nucleus.
Got it. And what defines one element from another? Is it just like their size or something more specific?
Yeah, it's actually remarkably precise. What truly distinguishes one chemical element from another is the number of protons in its atom's nucleus.
Just the proton count.
Just the proton count. Every single atom that contains, for instance, exactly 11 protons is sodium. No exceptions. Every atom with 29 protons is copper. It's that simple. The proton count acts as the atom's unique ID badge, basically.
Okay, clear. And you mentioned isotopes early on. What's the deal with those?
Ah, yes, isotopes. So these are atoms of the same element, meaning they share that identical proton count, but they differ in the number of neutrons they contain in the nucleus.
Same protons, different neutrons.
Exactly. And the seemingly small difference in neutron count can actually have profound effects on an atom's properties, particularly its stability, which we'll definitely explore later.
Okay, let's talk about the size then, because this is where my mind really starts to, well, boggle. We're talking about something unimaginably small here, right?
Oh, incredibly so. Atoms are truly microscopic, typically measuring only around 100 picometers across.
Picometers, that sounds tiny.
It is. To give you a sense of that scale, a picometer is 1/trillionth of a meter. That's a staggering 10 to the minus 10 meters.
Wow.
Imagine trying to observe something that minuscule. It really drives home the challenge scientists faced in even proving their existence, let alone studying them.
And that extreme smallness has massive implications beyond just how hard they are to see, doesn't it? Like, for physics.
It absolutely does. Their tiny size means we simply cannot see atoms with conventional optical microscopes because, well, they are much, much smaller than the shortest wavelength of visible light.
Right, light waves just pass over them.
Pretty much. But more profoundly, it means that the rules of classical physics, the physics we use to describe everything from a thrown ball to orbiting planets, they just break down at this scale.
They don't apply anymore.
Their behavior cannot be fully predicted by those familiar rules. Instead, we need quantum mechanics, because at this scale, the rules fundamentally change and quantum effects become dominant.
Okay.
And that's where the real mystery and, frankly, the wonder begin.
So get ready, everyone, because this is going to be a captivating journey. We'll cover the sweeping history of how we came to understand atoms, dive deep into their intricate internal structure, explore their surprising properties, and even trace their cosmic origins.
By the end of this deep dive, you'll be truly well informed about the very, very small.
All right, our deep dive begins by looking back, way back into the storied past of atomic theory. It's kind of wild to think that the basic idea that matter is made of tiny, indivisible particles isn't a new concept at all.
Not at all. It's incredibly ancient, actually, appearing in many different cultures across history.
Really? Like who?
Well, the Greeks are the most famous example. The very word atom comes to us from the ancient Greek word atomos,
Atomos.
meaning uncuttable or indivisible. This reflects that early philosophical notion that there must be some fundamental, irreducible unit of matter, a point beyond which you couldn't divide anything further.
Purely philosophical, though.
Exactly, and that's the crucial distinction. This ancient idea was based purely on philosophical reasoning and logical thought, not on scientific evidence or experimentation. Modern atomic theory, while it borrows the word, is built on a completely different foundation. It's based on, evidence.
So the big question becomes, how did we make that leap from just thinking about it, pure philosophical speculation, to concrete scientific understanding, something we could actually test and prove?
That's where we turn our attention to the early 1800s and the groundbreaking work of John Dalton. Dalton really marked a pivotal shift in scientific thought. He was a meticulous observer and, crucially, an experimentalist. By compiling experimental data, his own and data gathered by other scientists, he discovered a consistent pattern.
A pattern in chemical reactions.
Yes, specifically in how elements combine to form compounds. We now call it the law of multiple proportions.
The law of multiple proportions. And this law is really key to understanding how we moved from abstract ideas to concrete evidence, right?
Absolutely. What Dalton noticed was that whenever two elements combine to form more than one compound,
Like, say, carbon and oxygen making CO and CO2.
Precisely, or tin and oxygen, or iron and oxygen, he found that the ratios of the weights of one element that combined with a fixed weight of the other element would always be in simple whole number ratios.
Okay, that sounds a bit technical. Break that down.
It is a bit of a mouthful, but basically it meant that elements weren't just continuously mixing together like fluids. They seemed to be combining in multiples of basic discrete units.
Like tiny building blocks.
Exactly. And each element he proposed had a unit with a unique characteristic weight. Dalton then logically applied the ancient word atom to these fundamental units.
Okay, let's use an example because I think that helps.
Definitely. Let's illustrate this. Consider tin oxides. You can find two different types of compounds formed from just tin and oxygen. One is a gray powder and the other is a white powder.
Okay.
If you meticulously measure the composition, you'll find that for every 100 grams of tin in the gray powder, there's about 13.5 grams of oxygen.
13.5 grams of oxygen per 100 grams of tin.
Right. But in the white powder, for that same 100 grams of tin, there's about 27 grams of oxygen.
Exactly. Double. 13.5 and 27.
Exactly. So when Dalton looked at those numbers, 13.5 grams of oxygen in one, 27 grams in the other per the same amount of tin, what did that simple 1-to-2 ratio really tell him?
It couldn't just be a coincidence.
That's precisely where the aha moment hit. The fact that it was a simple 1.2 ratio, not some messy decimal like 1.2.37 or something, was incredibly powerful evidence.
Right.
It wasn't random. It strongly suggested that elements weren't just smearing together, but combining in discrete whole units. He concluded that this implied one atom of oxygen for every atom of tin in the gray oxide,
SNO.
and 2 oxygen atoms for every tin atom in the white oxide.
SNO2.
Exactly. This pattern simply wouldn't make sense if matter was infinitely divisible. It demanded particles.
And he saw this pattern again and again, right? Which must have really reinforced his idea.
Absolutely. Take iron oxides, for instance. You have a black powder and a red powder.
Like rust.
Well, related. When analyzed, for every 100 grams of iron in the black powder, there's about 28 grams of oxygen. But in the red powder, it's about 42 grams of oxygen for the same amount of iron.
Okay. 28 and 42. What's that ratio?
Well, if you divide both by 14, you get 2 and 3. The ratio here, 28 to 42, simplifies perfectly to 2.3.
Another simple whole number ratio.
Exactly. Dalton again deduced that for every 2 atoms of iron, there were either 2 or 3 atoms of oxygen corresponding to what we now know as FeO and F2O3. It's this consistent, small, whole number ratio that just screams discrete units.
Let's do one more just to really drive it home. Nitrogen oxides.
Oh, that's an even more striking example. You have nitrous oxide, laughing gas, nitric oxide, and nitrogen dioxide.
Okay.
If you normalize them all to a fixed amount of nitrogen, say 140 grams, then nitrous oxide has 80 grams of oxygen, nitric oxide has about 160 grams, and nitrogen dioxide has 320 grams.
160. 320. That's 1.2.4.
Perfect. This was hugely significant. It strongly suggested simple formulas like N2O, NO, and NO2, unambiguously demonstrating that these elements combined in discrete whole number units.
This was truly revolutionary, wasn't it?
Oh, absolutely. Dalton's work provided the first truly scientific, experimentally verifiable evidence for the existence of atoms. It moved the concept from just philosophical speculation to a testable scientific theory.
And for a long time after this, atoms were still thought to be the smallest, most fundamental particles, right?
Yeah.
Indivisible, like the name suggests.
That was the prevailing view, but then, then things got really interesting.
You can say that again, because for decades, the atom was pictured as this solid, indivisible billiard ball. But in the late 19th century, that idea just shattered.
It did, with the debut of the electron.
Tell us about that discovery.
Okay, so in 1897, a physicist named J.J. Thomson was conducting fascinating experiments with cathode rays.
Cathode rays, those are beams in vacuum tubes.
Exactly. Beams generated in a vacuum tube. He observed that these rays could be deflected by both electric and magnetic fields.
Which
was crucial. It proved that cathode rays weren't just a form of light, as some thought, but were actually composed of electrically charged particles. And given the direction of the deflection, they had to be negatively charged.
He initially called these mysterious new particles corpuscles, right?
He did. A bit of an old-fashioned term. They were later, and much more famously, renamed electrons because, well, they carried electric charge.
But the truly shocking part wasn't just that they existed. It was their mass, wasn't it?
Oh, absolutely. Thomson managed to measure their mass-to-charge ratio, and he found these particles were about, well, estimates varied, but roughly 1,700 to 2,000 times lighter than hydrogen, which was the lightest known atom at the time.
Lighter than the lightest atom, that's huge.
It was monumental. It implied that atoms were not indivisible, they had internal structure, they contained even smaller particles. It was a complete paradigm shift.
So this immediately posed a new problem for Thomson, right? If atoms have negative bits inside, but are neutral overall.
Exactly. If atoms contained these tiny, negatively charged electrons, but atoms themselves were generally electrically neutral, then there had to be an equal amount of positive charge somewhere inside to balance them out.
So how did he picture it?
Well, Thomson proposed what's popularly known as the plum pudding model of the atom.
Plum pudding, like the dessert.
Sort of. He imagined the atom as a sphere of diffuse, positively charged pudding with the tiny negative electrons embedded within it, much like plums scattered through a pudding.
It sounds kind of charming, actually, the plum pudding atom. A bit simplistic, maybe?
It was simple and charming, yes. But despite its simplicity, it had significant limitations. This model couldn't explain many observed properties of elements, like their unique emission spectra, those distinct patterns of light they give off when heated.
Or how they bond together.
Right, or how they formed chemical bonds, their valencies. It just didn't count for that structure. It was quickly rendered obsolete, really, by the next big discovery.
Okay, so the positive charge wasn't just a diffuse pudding. The question remained, where was that positive charge truly hiding, and how was it distributed?
Precisely. And that's what Ernest Rutherford and his colleagues, Hans Geiger and Ernest Marsden, set out to discover in the early 20th century, between about 1908 and 1913.
This is the famous gold foil experiment, isn't it?
That's the one. They performed what became known as the gold foil experiment. They bombarded extremely thin foils of metal, particularly gold, because you can make it incredibly thin with a beam of positively charged alpha particles.
Alpha particles, those were like tiny bullets.
Helium nuclei, right?
Exactly, helium nuclei, positively charged. And if Thomson's plum pudding model was right, those alpha particles should have just sailed straight through the thin foil, shouldn't they? Maybe a tiny deflection here and there, but nothing major.
Because the positive charge was spread out, too weak to push them back? Exactly. The plum pudding model predicted only negligible deflections because the charges were just too spread out, too diffuse for any substantial interactions to occur.
But that's not what they saw, was it?
Not at all. What they observed was truly unexpected and, frankly, revolutionary. While most alpha particles did pass straight through, as expected, a small number, about 1 in 8,000, were deflected at angles greater than 90 degrees, and some, incredibly, even bounced straight back.
Bounced back from thin gold foil.
Rutherford himself famously compared it to firing a 15-inch naval shell at a piece of tissue paper and having it come back and hit you.
Wow, that's a powerful image.
It was astonishing. That observation utterly challenged Thomson's model. It simply couldn't account for such extreme deflections.
So Rutherford had to come up with something completely different.
He did. He came up with a revolutionary new idea. The positive charge and almost all of the atom's mass must be concentrated in a tiny, incredibly dense volume at the very center of the atom.
Not spread out pudding, but a tiny core.
Exactly. He called this the nucleus. The electrons, he proposed, surrounded this nucleus in a diffuse cloud much further out, occupying mostly empty space.
And only that dense positive charge could repel the alpha particles so strongly.
Precisely. Only such an incredibly intense concentration of charge, anchored by nearly all the atom's mass, could create an electric field strong enough to deflect those positively charged alpha particles so dramatically. This experiment gave us the first clear picture of an atomic nucleus.
But then physics threw up another problem, didn't it? The classical physics problem.
Ah, yes, the stability issue. If electrons orbit this nucleus like planets around a sun, well, classical electromagnetism dictates that an accelerating charged particle, like an orbiting electron, should continuously radiate energy.
Losing energy.
And as it loses energy, it should spiral closer and closer to the positive nucleus until, poof, the atom collapses.
But atoms don't collapse, they're stable. So classical physics was wrong here.
It was a massive contradiction. And this is where Niels Bohr made his quantum leap in 1913.
Bohr's model. What was his solution?
Bohr's solution was both brilliant and, well, deeply counterintuitive from a classical perspective. He proposed that electrons could only orbit the nucleus in a finite set of specific allowed orbits, or what we now call energy levels.
Only certain paths were allowed, like steps on a staircase.
Exactly. This was a radical idea of quantization. He said electrons could only jump between these allowed orbits by absorbing or radiating a photon, a packet of light energy with a discrete amount of energy, precisely matching the energy difference between the orbits.
No sliding down the ramp, only jumping between steps.
Perfectly put, no in-between states were allowed.
And what did this explain?
Well, right away, it explained why electron orbits are stable. They simply can't lose energy continuously by spiraling because there are no allowed orbits in between. And it also explained why elements absorb and emit electromagnetic radiation in distinct, discrete spectra, those unique fingerprints of light. Each line in the spectrum corresponds to an electron jumping between two specific allowed energy levels.
That was a huge step forward in understanding atomic stability and spectroscopy.
Absolutely massive. But even Bohr's model, brilliant as it was, had its limitations.
It wasn't the final answer.
It worked beautifully for hydrogen, the simplest atom with just one electron. But it struggled to accurately predict the spectra of more complex atoms with multiple electrons. The interactions were just too complicated for his model.
So we were getting closer to the true picture, but something was still missing, particularly from the nucleus itself.
Indeed. The full nuclear picture really started coming into focus with the discovery of the other key players, protons and neutrons.
Right, the nucleus wasn't just positive charge, it had structure.
Exactly. Going way back to 1815, actually, a chemist named William Prout observed that the atomic weights of many elements seemed to be simple multiples of hydrogen's atomic weight.
Suggesting hydrogen was a building block.
That was his hypothesis, yes, though later refined to account for isotopes. Then, J.J. Thomson, our electron discoverer, followed up in 1898, finding that the positive charge of a hydrogen ion was equal in magnitude to the negative charge of an electron.
Suggesting a basic unit of positive charge.
Then, in 1913, the same year as Bohr's model, Henry Moseley's work with X-rays was critical. He found a clear mathematical relationship between the frequencies of X-ray emissions from an excited atom and its atomic number.
Linking X-rays to something fundamental in the atom.
Yes, essentially linking this atomic number to the positive charge in the nucleus, using hydrogen's nuclear charge as the unit.
And Rutherford comes back into the story now.
He does. In 1919, Rutherford was bombarding nitrogen gas with alpha particles, remember his earlier experiment, and he noticed hydrogen ions being emitted.
Hydrogen coming out of nitrogen.
Yes. He concluded that these hydrogen nuclei were being knocked out from inside the nitrogen atoms, suggesting they were a fundamental component of heavier nuclei. By 1920, he had confirmed that the hydrogen nucleus was a singular, positively charged particle, and he formally named it the proton.
The first nucleon identified.
Exactly. And Rutherford's atomic number, which was simply the number of protons, provided a clear, fundamental way to distinguish one chemical element from another. Finally, a proper definition based on internal structure.
But there was still a puzzle, right? The mass didn't add up.
Precisely. The missing mass problem. Atomic weights were consistently higher, often about double, than their proton numbers alone could account for. Helium, for example, has 2 protons, but an atomic weight of about 4.
So something else heavy must be in there.
That led Rutherford to hypothesize that there must be another unknown particle in the nucleus, a neutral one, with a mass very similar to that of a proton to make up the difference.
Enter the neutron.
And that's where James Chadwick enters in 1932. The story actually begins a few years earlier, around 1928, when Walter Bothe observed that beryllium, when bombarded with alpha particles, emitted a highly penetrating, electrically neutral radiation.
Neutral radiation, like gamma rays.
That was the initial thought, high-energy gamma radiation. But Chadwick, in 1932, did some clever experiments. He exposed various elements like hydrogen and nitrogen to this mysterious beryllium radiation. By measuring the energies of the recoiling charged particles the protons knocked out of the hydrogen, for instance, he deduced that this radiation was far too energetic, too heavy to be massless gamma rays.
It had momentum, mass.
Exactly. It had to be composed of electrically neutral particles, but particles with a mass very similar to that of a proton. Chadwick then famously confirmed Rutherford's hypothesized neutral particle, naming it the neutron.
And with the proton, neutron, and electron finally identified, we had the basic components of the atom nailed down. The ingredients were known.
We had the ingredients. But the real question then became, how do these particles truly behave? Because the simple planetary models, even Bohr's quantized orbits, just weren't cutting it for explaining all the observations, especially for more complex atoms.
This is where things get really weird, isn't it? Quantum mechanics weird.
This ushered in the era of quantum mechanics, which gave us our current and much stranger consensus model of the atom. In 1924, Louis de Broglie proposed the revolutionary idea of wave-particle duality.
Everything is both a particle and a wave.
Essentially, yes. He proposed that all particles, including electrons, behave like waves to some extent, with a wavelength related to their momentum.
Okay.
Building on this, in 1926, Erwin Schrödinger developed his famous equation. He used de Broglie's idea to describe electrons not as distinct points orbiting a nucleus, but as three-dimensional waveforms, like standing waves.
Electrons as waves, not tiny balls.
Mathematically, yes. And this wave-like nature had profound consequences. In 1927, Werner Heisenberg formulated his uncertainty principle.
The famous one, can't know everything precisely.
Right. It's a direct mathematical consequence of using waveforms to describe particles. It states that it's fundamentally impossible to know both the precise position and the precise momentum of a particle at the same time. Because the more accurately you try to measure one, like pinning down the position of a wave, the more spread out or uncertain the other becomes, like the wave's momentum. It's an inherent property of the wave nature.
Mind-bending.
It really is. So the simple, intuitive planetary model of electrons orbiting the nucleus like planets around the sun, even Bohr's version, had to be discarded. It just wasn't reality.
So what's the modern picture then, if not orbits?
The modern model describes atomic orbitals. These aren't paths, but rather mathematical functions that describe zones or regions around the nucleus where an electron is most likely to be found. It's a probabilistic picture, a cloud of probability density, not a deterministic orbit.
Probability clouds instead of orbits.
Exactly. And this quantum mechanical model was incredibly successful. It finally explained observations of atomic behavior that all previous models couldn't, including the complex structural arrangements and spectral patterns for larger multi-electron atoms. It was a complete paradigm shift in how we understand matter at its most fundamental level.
Wow. So now that we've journeyed through this incredible history, from ancient philosophy all the way to the probabilistic world of quantum mechanics, let's zoom in even further. Let's really look at the atom's internal architecture, its inner workings, based on this modern view.
Absolutely. And it's funny, the very word atom, which originally meant uncuttable, is now beautifully ironic, isn't it?
Yeah, because now we know.
In modern scientific usage, an atom is definitively known to be divisible. It's composed of smaller subatomic particles, the electron, the proton, and the neutron being the main players.
Let's start with the electron again. What makes it so unique among these three?
Well, the electron is by far the lightest of the three primary particles, about 1,836 times less massive than a proton.
Much lighter.
Much lighter. It carries a negative electrical charge, and intriguingly, its size is still considered too small to be measured using current techniques. It's treated as an elementary particle in the standard model.
Meaning no internal structure. It's fundamental.
As far as we know, yes. It has no known internal structure. Under normal conditions, electrons are bound to the positively charged nucleus by that electromagnetic attraction we talked about.
And if an atom gains or loses electrons?
Then it becomes electrically charged, forming an ion. An anion, if it has an excess of electrons, more negative. A cation, if it has a deficit, more positive.
Okay, and then we have the heavyweights in the nucleus.
Yeah,
Protons and neutrons.
exactly. The proton carries a positive charge, equal in magnitude to the electron's negative charge. And it has a mass much larger than the electron, setting the scale for atomic mass.
And its number defines the element.
Correct. As we discussed, the number of protons fundamentally defines the atomic number Z of an atom, identifying the element. The neutron, discovered later because it lacks electrical charge, is just a tiny bit heavier than the proton.
Slightly heavier. Interesting.
Yeah, although its effective mass can be slightly reduced when it's bound inside a nucleus due to the nuclear binding energy mass being converted to energy, essentially.
EMC2 again.
Always lurking. And protons and neutrons are collectively called nucleons. They are roughly similar in size, incredibly small, on the order of a few femtometers, 10, 15 meters.
But the rabbit hole goes even deeper. You mentioned earlier. Are these particles truly elementary? Protons and neutrons.
Ah, good catch. Not entirely. According to the standard model of particle physics, while electrons are considered elementary particles,
No parts inside.
protons and neutrons are actually composite particles. They are made up of even smaller, more fundamental elementary particles called quarks.
Quarks. So protons and neutrons are like tiny Lego constructions themselves, made of quarks.
Precisely. It's a great analogy. There are 6 types or flavors of quarks, but only 2 types are found within everyday stable matter, up quarks and down quarks, and they possess a rather strange property: fractional electric charge.
Fractional charge, not whole number.
Nope. An up quark has a charge of plus 23, positive 2/3 of the elementary charge, while a down quark has a charge of negative 13, negative 1/3.
Okay, so how do they make a proton and a neutron?
A proton is composed of 2 up quarks and 1 down quark. So that's plus 23 plus plus 23 plus 43 13 plus 43 13 plus 33 plus 1, a total charge of plus 1.
Makes sense. And the neutron?
Neutrons consist of 1 up quark and 2 down quarks. So that's plus 23 plus negative 13 plus 23 equals 0, a total charge of 0.
Wow, it works out perfectly. That quark composition accounts for their charge and also contributes to their mass difference.
It does. And what binds these quarks together inside the proton and neutron, it's the strong interaction or strong nuclear force, which is mediated by particles called gluons.
Gluons, like glue.
Exactly like glue. And here's a key point. The nuclear force that binds protons and neutrons together within the nucleus is actually a residuum, a sort of leftover effect of this much stronger force holding the quarks themselves together inside the nucleons.
Incredible layers of forces and particles. So from these elementary particles, quarks, and electrons, we build up the atom's core, the nucleus. This is truly the atom's dense heart.
Indeed. All the bound protons and neutrons, the nucleons, in an atom combine to form this incredibly tiny atomic nucleus. And when we talk about tiny, we really mean it.
How tiny compared to the whole atom?
The nucleus's radius is on the order of femtometers, which is 10, 15 meters. To put that in perspective, the entire atom, defined by its electron cloud, is about 100,000 times larger in radius than its nucleus.
100,000 times. So if an atom were the size of a football stadium.
The nucleus would be no bigger than a pea sitting on the center spot. The vast majority of an atom's volume is the electron cloud, mostly empty space, relatively speaking.
Okay, that's staggering. And what holds this incredibly dense collection of positively charged protons together in that tiny pea? Given that, charges repel each other so powerfully, shouldn't it fly apart?
An excellent question. That's where the residual strong force, also known simply as the nuclear force, comes in again. It's a short-range but very powerful attractive force that acts between nucleons, proton-proton, neutron-neutron, and proton-neutron.
Stronger than the repulsion?
At very short distances, yes. Less than about 2.5 femtometers. This attractive force is immensely more powerful than the electrostatic repulsion between the positively charged protons. This dominance of the strong force over electrostatic repulsion at these tiny distances is absolutely crucial for nuclear stability. If it weren't stronger, nuclei couldn't exist.
And this balance of forces also plays a role in defining elements and isotopes, right?
Absolutely. We've already established that the atomic number, the number of protons, defines the element. But within that element, atoms can have different numbers of neutrons, making them isotopes. A specific combination of protons and neutrons is called a nuclide. like carbon-12 or carbon-14.
And the ratio of neutrons to protons within that nuclide is critical for stability.
Very critical. It determines the stability of the nucleus. Certain combinations are highly stable, while others are unstable and undergo radioactive decay to reach a more stable state.
There's also another fundamental principle at play here, isn't there? Something about particles not liking to be in the same state.
Ah, yes, the Pauli exclusion principle. It's fundamental. Protons, neutrons, and electrons are all classified as fermions. And fermions obey this principle, which dictates that no two identical fermions can occupy the same quantum state at the same time within the same system, like an atom.
So every particle needs its own unique address.
In a sense, yes. Within an atom, every proton, every neutron, and every electron must have a unique set of quantum numbers describing its state, like energy level, spin, etc. This principle is fundamental to atomic structure and helps explain how electrons arrange themselves in shells and orbitals around the nucleus, and also how nucleons arrange themselves within the nucleus.
And this principle also helps explain why neutrons are so key for nuclear stability, especially in heavier elements.
Precisely. As the atomic number increases, you have more and more protons packed into that tiny nucleus. Their mutual electrostatic repulsion becomes increasingly significant and threatens to tear the nucleus apart.
So neutrons act like nuclear glue.
You could think of it that way. To counteract this growing repulsion and maintain stability, more neutrons are needed. Neutrons contribute to the attractive, strong nuclear force holding the nucleus together, but they don't add any electrostatic repulsion because they're neutral. So heavier, stable nuclei always have more neutrons than protons.
And nuclei with imbalanced proton-neutron ratios just decay.
Often, yes. They decay through various radioactive processes to try and reach a more stable, lower energy configuration.
Okay, so the nucleus isn't just a static core. Its number of protons and neutrons can be modified, though it requires immense energies due to the strength of that nuclear force. This leads us to two incredibly powerful processes: nuclear fusion and nuclear fission.
Let's start with fusion. Nuclear fusion is what powers the stars, including our own sun. It occurs when multiple atomic particles, typically light nuclei like hydrogen isotopes, join together under extreme temperature and pressure to form a heavier nucleus.
Like hydrogen fusing into helium in the sun.
Exactly. But for this to happen, the nuclei need tremendous kinetic energy temperatures of millions of degrees to overcome their mutual electrostatic repulsion, that Coulomb barrier we mentioned. They need to get close enough for the short-range, strong force to take over and bind them.
And this is where Einstein's famous equation, EMC2, really shines, isn't it? That mass-energy conversion.
It's central to it. If the mass of the newly fused nucleus is slightly less than the sum of the masses of the individual particles that went into it,
which it often is for light elements.
Right, there's a mass deficit. That missing mass hasn't vanished. It's been converted directly into energy according to EMC2. This energy is released, often as high-energy photons like gamma rays, or as the kinetic energy of emitted particles like neutrons or neutrinos. This released energy is what we call the binding energy of the new nucleus.
And the fusion of lighter nuclei, say up to iron, is usually exothermic, right? It releases energy.
That's correct. Fusion that creates nuclei with atomic numbers up to about 26 iron, or mass numbers up to about 60 iron and nickel, generally releases more energy than is required to initiate it. The binding energy per nucleon increases up to iron. This is why nuclear fusion in stars is a self-sustaining reaction, and why stars can shine for billions of years.
But what happens beyond iron? Can stars fuse heavier elements?
Not energetically favorably. For nuclei heavier than iron and nickel, the binding energy per nucleon actually starts to decrease. This means that if you try to fuse nuclei to create elements heavier than iron, the process becomes endothermic. It actually requires an input of energy rather than releasing it.
So fusion stops being an energy source for the star.
Exactly. And this is precisely why stars effectively stop fusing elements at iron. They can't get any more energy out of fusion beyond that point. The creation of heavier elements requires different, more energetic processes like supernovae.
Okay, so that's fusion. What about nuclear fission? The opposite process.
Nuclear fission is indeed the opposite. A heavy, often unstable nucleus splits into two or more smaller nuclei, often accompanied by the release of neutrons and a significant amount of energy, again due to mass being converted. This can happen spontaneously for some very heavy isotopes, or it can be induced, for example, by bombarding a nucleus like uranium-235 with a neutron.
And this is the basis for nuclear power and weapons.
It is. Both fusion and fission, if they result in a change in the number of protons in the nucleus, can actually transform one atom into a different chemical element. This is true transmutation, the dream of the alchemists, achieved through nuclear physics.
So the nucleus holds almost all the atom's mass and dictates its very identity and potential for these huge energy releases. But it's the electron cloud surrounding it that determines how atoms interact chemically, right? How they form molecules and materials.
Absolutely. The nucleus is the heart, but the electrons are where the chemical action happens. This is truly where chemistry lives.
How are they held there again?
The electrons are held in place, loosely speaking, orbiting the nucleus in those probability clouds, by the electromagnetic force, the attraction between their negative charge and the positive charge of the protons in the nucleus.
Trapped.
You can think of them as being trapped in an electrostatic potential well. This means that a certain amount of external energy is needed for an electron to escape the atom entirely, a process called ionization. The closer an electron is to the nucleus, in a lower energy level, the stronger the attraction, and therefore the more energy it takes for that electron to escape. This energy is called the binding energy of the electron.
And this is where the particle-wave duality of electrons really becomes crucial again, right? They're not just particles orbiting.
Correct. Electrons behave as both particles and waves simultaneously. The electron cloud isn't just a random swarm, it's better visualized as a region where each electron forms a specific type of three-dimensional standing wave around the nucleus.
Standing wave, like on a guitar string.
Kind of analogous, yes. These wave patterns don't move relative to the nucleus in the way a traveling wave would. Their shape and location are described by what we call an atomic orbital.
And an orbital isn't a path, it's a probability map.
Exactly. An atomic orbital is a mathematical function derived from the Schrödinger equation that describes the probability of finding an electron at a particular location around the nucleus. It's a cloud of probability, densest where the electron is most likely to be found.
And like Bohr suggested, only certain orbitals, certain wave patterns are allowed.
Precisely. Only a discrete or quantized set of these orbitals, each corresponding to a specific energy level, exists stably around the nucleus. Other possible wave patterns simply aren't stable solutions to the Schrödinger equation for that atom and rapidly decay or transform into a stable orbital shape.
Each orbital has a specific energy level, and this leads to incredibly specific interactions with light, right? Photons.
Absolutely. For an electron to transition from a lower energy orbital to a higher energy one, it must absorb a photon, a particle of light, with precisely the right amount of energy, exactly matching the energy difference between those two orbitals.
It has to be the exact right color of light, essentially.
Essentially, yes, the exact right frequency or energy. Likewise, an electron in a higher energy state, an excited state, can drop down to a lower vacant energy state by emitting a photon, carrying away that exact energy difference.
And these jumps are particle-like. One photon, one electron.
Yes, the interaction is quantized. One photon interacts with one electron, causing it to jump between orbitals in a seemingly instantaneous, particle-like fashion.
What's truly significant here is that the energy of an emitted photon is directly proportional to its frequency, or inversely proportional to its wavelength. So these specific quantized energy level differences within an atom result in the emission or absorption of light at very specific frequencies or wavelengths.
And this creates that unique fingerprint spectrum for each element we talked about earlier. It's how we can identify elements even across billions of light years in distant stars just by analyzing the light they emit or absorb.
And just to really hammer home the difference in scale between chemical energy and nuclear energy, let's compare the energy needed to remove an electron versus splitting a nucleus.
Oh, the difference is absolutely massive. It highlights the relative strengths of the electromagnetic force holding electrons versus the strong nuclear force holding the nucleus together.
Give some numbers.
Okay. For example, it only takes a relatively tiny amount of energy, about 13.6 electron volts eV, to strip the single ground state electron from a hydrogen atom to ionize it.
13.6 eV.
But to split a deuterium nucleus, one proton, one neutron, into its constituent proton and neutron, it takes about 2.23 million electron volts.
Million.
Yeah.
Compared to 13.6.
Wow. Yeah, we're talking about a difference of more than 160,000 times. That massive difference in energy scales is precisely why nuclear reactions release vastly more energy than chemical reactions.
because chemical reactions only involve rearranging those outer electrons.
Right, involving energies on the order of electron volts per atom. While nuclear reactions involve changes within the nucleus, tapping into that incredibly strong nuclear binding energy, releasing millions of electron volts per nucleus.
Got it. And speaking of chemical reactions involving electrons, electrically neutral atoms have an equal number of protons and electrons, but atoms with a deficit or surplus of electrons are, as we said, called ions.
Correct. Anions are negative ions, gained electrons. Acations are positive ions, lost electrons.
And these electrons, particularly those in the outermost energy levels, the valence electrons, are the true drivers of chemistry, aren't they?
They absolutely are. Electrons farthest from the nucleus, the valence electrons, are less tightly bound and are the ones that participate in forming chemical bonds with other atoms. They can be transferred from one atom to another, forming ionic bonds.
Like in table salt, sodium chloride. Sodium gives, chlorine takes.
Exactly. Sodium loses its single valence electron to become Na plus F. Chlorine gains an electron to fill its outer shell and become Cl, and the positive and negative ions attract. Or valence electrons can be shared between atoms,
Covalent bonds.
forming covalent bonds, which is how most molecules are held together, like water, H2O, or methane, CH4, or the complex structures in organic chemistry built around carbon.
In this fundamental drive for atoms to react to either fill or empty their outer valence shells to achieve a more stable electron configuration, usually like that of a noble gas, is the underlying reason for all chemical bonding, right?
That's the fundamental principle. It's what drives the formation of molecules, crystals, ionic compounds, and all the diverse substances that make up our world.
And it's why the periodic table is so incredibly useful and predictive. It's organized based on this electron structure.
Precisely. Elements with the same number of valence electrons have similar chemical properties and are therefore grouped in the same vertical column or group of the periodic table. Think of lithium, sodium, potassium, all highly reactive metals with one valence electron.
And the horizontal rows, the periods.
The horizontal rows correspond to the filling of successive electron quantum shells, or energy levels. As you move across a row, you're adding electrons to the same principal energy level,
Until you reach the far right.
where you find the noble gases like helium, neon, argon. They've completely filled outer valence shells, which is an extremely stable electron configuration. And that's why they are so famously chemically inert or unreactive. They generally don't need to gain, lose, or share electrons.
It's truly the social life of atoms, governed by their electrons.
Okay, with the structure and fundamental interactions now defined, let's pivot to explore the incredible properties and behaviors these tiny particles possess, starting with the nuclear characteristics, stability, and diversity.
All right, so starting with the basics of identity again. By definition, as we've hammered home, any two atoms with an identical number of protons in their nuclei belong to the same chemical element. That's non-negotiable.
Proton number equals identity. Exactly. However, as we also discussed, atoms of the same element can have different numbers of neutrons. These are the different isotopes of that element.
Like hydrogen 1, hydrogen 2, hydrogen 3.
Precisely. Hydrogen atoms all have one proton, but you have protium, the most common form, with no neutrons, deuterium with one neutron, and tritium with two neutrons. Same element, different isotopes, different mass, and sometimes very different stability. Tritium is radioactive, for instance.
Okay, and the spectrum of known elements is vast, right? From hydrogen up to...
It ranges from hydrogen element number 1 all the way up to the currently heaviest confirmed element, oganesson, element number 118 Vin.
118 protons, wow.
And it's quite interesting to note a general trend. All known isotopes of elements with atomic numbers greater than 82, which is lead, are radioactive.
Everything heavier than lead is unstable.
Essentially, yes. Although for element 83, bismuth, its most common isotope, bismuth 209, has such an incredibly long half-life, billions of times the age of the universe, that it's often considered practically stable for most purposes. But technically, it does decay.
So it's a vast family of atoms, hundreds of unique combinations of protons and neutrons, which we call nuclides. But what's truly fascinating, though, is how few of these combinations, these nuclides, are actually stable in the long run.
That's a key point. There are about 339 nuclides known to exist naturally on Earth. Of those, only about 251 are considered stable isotopes, meaning their radioactive decay has never been observed.
Never observed, so they might still decay, just incredibly slowly.
Exactly. In fact, only about 90 of those 251 are thought to be theoretically stable against all forms of decay. The rest are considered observationally stable, meaning their predicted half-lives are just so immensely long, often far longer than the current age of the universe, that we simply haven't seen them decay yet.
That's a really interesting distinction.
Yeah.
Truly stable versus observationally stable. It really puts into perspective the resilience of certain atomic structures versus others and the vast timescales involved.
It does. The remaining naturally occurring nuclides are radioactive. These include about 35 long-lived radioactive nuclides that are primordial. They've been around since the solar system formed, like uranium-238 or potassium-40.
Still decaying from the beginning.
Yep. And then there are about 53 shorter-lived radioactive nuclides found naturally, but these exist because they are either decay products of the long-lived ones, like radium from uranium decay, or they are constantly being generated by natural processes, like cosmic ray interactions.
Like carbon-14.
Carbon-14 is the perfect example, constantly being produced in the upper atmosphere. That's why it's so useful for dating organic materials up to about 50,000 years old.
So overall, most elements we know have at least one stable isotope.
Yes, 80 of the first 82 elements up to lead have at least one stable isotope. Tin, element 50, has the most, with 10 stable isotopes.
10. Why so many for 10?
That relates to what we call magic numbers. The number 50 is a magic number for protons. Nuclei with a magic number of protons or neutrons tend to be unusually stable because they represent filled quantum shells within the nucleus, analogous to the filled electron shells in noble gases that provide chemical stability.
Nuclear shells, just like electron shells. Fascinating.
It's a similar concept, so factors affecting stability include not just the overall proton-to-neutron ratio, but also these magic numbers, and whether the numbers of protons and neutrons are even or odd.
Even or odd makes a difference.
It does. Nuclei with even numbers of protons and even numbers of neutrons, even nuclei, tend to be the most stable. Nuclei with odd numbers of both, odd nuclei, are generally the least stable and often decay quickly.
Are there any stable odd nuclei?
Very few naturally occurring stable ones. Only 4 light ones exist. Deuterium, hydrogen-2, lithium-6, boron-10, and nitrogen-14. Most other odd nuclides are highly unstable.
Okay, so a complex interplay of factors determines stability. Now, how do we actually quantify these tiny packages of matter? How do we weigh the invisible?
Well, as we know, the vast majority of an atom's mass comes from its protons and neutrons in the nucleus. The electrons contribute very little.
So we focus on the nucleons.
Right. We use the mass number, symbol A, to simply count the total number of nucleons, protons, plus neutrons in a given nuclide. It's just a count, so it's a dimensionless positive integer. For example, carbon-12 has 6 protons and 6 neutrons, so its mass number is 12. Carbon-14 has 6 protons and 8 neutrons, mass number 14.
Simple enough. But for actual mass measurement in labs, scientists use a special unit, right? Not kilograms.
Correct. Kilograms are far too large and inconvenient. The standard unit for atomic masses is the Dalton, symbol Day, which is also called the Unified Atomic Mass Unit, symbol U.
How is it defined?
It's defined as exactly 112th the mass of a single, free, neutral carbon-12 atom in its nuclear and electronic ground state. So carbon-12 has a mass of exactly 12 Daltons by definition.
And other atoms, are their masses nice whole numbers in Daltons?
Approximately, but not exactly, except for carbon-12. An atom's atomic mass, its actual mass in Daltons, is approximately equal to its mass number, but there are small deviations due to the mass difference between protons and neutrons and the effect of nuclear binding energy. The EMC2 part, again, mass converted to energy when the nucleus forms.
So hydrogen-1 isn't exactly 1 Dalton.
Correct. Hydrogen-1, a single proton and electron, is the lightest nuclide, with a mass of about 1.00007825 Day. The heaviest stable nuclide is lead-208, weighing in at about 207.9766521 Day.
Still incredibly tiny masses. So how do chemists actually work with these in practice?
They use a concept that bridges the microscopic and macroscopic worlds, the mole.
The mole, Avogadro's number.
Exactly. Because even the most massive atoms are still far too light to weigh out individually, chemists work with huge numbers of them. 1 mole of atoms of any element always contains the same incredibly large number of atoms. That number is Avogadro's number, which is approximately 6.022 particles per mole.
A ridiculously huge number. Why that specific number?
It's chosen very deliberately. Avogadro's number is defined such that if an element has an atomic mass of X Daltons, then 1 mole of atoms of that element will have a mass of approximately X grams.
It connects Daltons to grams.
Precisely. For instance, since carbon-12 has an atomic mass of exactly 12 DAF, 1 mole of carbon-12 atoms weighs exactly 12 grams, which is 0.012 kilograms, the official SI definition. For other elements, it's very close. 1 mole of hydrogen atoms, mostly H1, weighs about 1 gram. 1 mole of oxygen atoms, mostly O16, weighs about 16 grams.
It's like the chemist's dozen, but a much, much bigger dozen. It makes atomic masses practical for lab work.
That's exactly what it is. It allows us to weigh out macroscopic quantities of substances in grams and know how many atoms or molecules we're dealing with in moles.
Okay, so from the atom's mass, let's shift our focus to its physical dimensions. We often think of atoms as tiny, perfect spheres, but you suggested earlier that's maybe just a convenient simplification. What about their actual shape and size?
That's a great question. And yeah, it reveals another subtle complexity. Atoms actually lack a well-defined outer boundary. The electron cloud doesn't just abruptly stop.
It just sort of fades out.
Exactly. The probability of finding an electron decreases with distance, but never truly reaches zero. So defining a size is tricky. Their dimensions are typically described in terms of an atomic radius.
But how do you measure the radius of something fuzzy?
There are different ways to define it, depending on the context. It might be half the distance between the nuclei of 2 identical atoms bonded together, covalent radius, or the radius in a metallic crystal, metallic radius, or an estimate for an isolated atom, van der Waals radius. It essentially measures how far the electron cloud effectively extends from the nucleus.
And this radius isn't fixed for a given element.
No, it's not fixed. It varies depending on the atom's position on the periodic table, generally increasing as you move down a column, adding more electron shells, and decreasing as you move across a row from left to right. Increasing nuclear charge pulls electrons closer. It also depends significantly on the type of chemical bond the atom is forming, the number of neighboring atoms, coordination number, and even a quantum mechanical property called spin.
So what are the smallest and largest atoms we know, roughly?
The smallest neutral atom is helium, with a calculated radius of around 32 picometers, that's 32 trillionths of meter. One of the largest is cesium, down on the bottom left of the periodic table, with a radius around 225 picometers. Still incredibly tiny.
And you mentioned they aren't always perfectly spherical. They can get squashed or stretched.
That's right. While an isolated atom in free space would be spherical, atoms can deviate from spherical symmetry when they are subject to external forces, like strong electrical fields, or, more commonly, when they are packed together in a crystal lattice or involved in certain types of chemical bonds.
Can you give an example?
Sure. For instance, sulfur ions and other chalcogen ions, when they are part of pyrite-type crystal compounds, have been shown to exhibit significant ellipsoidal shapes. They look more like tiny, slightly flattened footballs than perfect spheres due to the specific bonding environment.
Okay, now here's where it gets really interesting again, trying to visualize just how minute these things are. You said atoms are thousands of times smaller than the wavelengths of visible light.
Correct. Visible light wavelengths are typically 400–700 nanometers. Atomic radii are in picometers thousands of times smaller.
Which means you simply cannot see them with conventional optical microscope, no matter how powerful. The light waves just diffract around them without resolving detail.
Exactly. Yet, as we'll discuss more in Part 4, we can see individual atoms on solid surfaces using specialized equipment, like the Scanning Tunneling Microscope, STM. It doesn't use light, but quantum effects.
Okay, so let's try some analogies again to truly grasp the scale. A human hair.
A typical human hair is about 1 million carbon atoms wide. Think about that, lining up 1 million atoms side by side just to match the width of a single hair.
Mind-blowing. A drop of water.
If you take a single drop of water, it contains an astounding 2 sextillion, that's 2, followed by 21 zeros oxygen atoms, and twice that many hydrogen atoms. 2 by 1021 oxygen atoms.
The numbers are just astronomical. A diamond.
A 1-carat diamond, which weighs only 0.2 grams, contains about 10 sextillion carbon atoms. That's 122 atoms.
Okay, here's one of my favorite analogies. The apple one. Run that by us again.
Right, the apple analogy really helps visualize the emptiness too. Imagine an apple. Now imagine magnifying that apple until it's the size of the entire Earth.
Okay, huge apple.
Now, if you could then look at the atoms within that Earth-sized apple, each individual atom would be approximately the size of the original apple.
Whoa, so the space between the nucleus and electrons is vast compared to their size.
Immense. That gives you a sense of just how much empty space there is within matter and how incredibly dense the nucleus must be to contain nearly all the mass in that tiny volume. It almost makes you feel insubstantial, doesn't it?
It definitely puts things in perspective. All that seemingly solid stuff around us is mostly quantum fuzz in empty space.
Ugh.
But that empty space isn't really empty. It's where the quantum dance of electrons happens.
Precisely. And that brings us to the fact that some atoms, particularly those with unstable nuclei, aren't content to simply exist in these minuscule forms. They undergo dramatic transformations. This brings us back to radioactive decay.
Right, when atoms spontaneously change their identity by ejecting particles or energy from the nucleus.
Exactly. As we said, every element has one or more isotopes with unstable nuclei that undergo radioactive decay. Essentially, radioactivity occurs when the nucleus is too large or has an unfavorable proton-to-neutron ratio, straining the balance between the repulsive electromagnetic force between protons and the attractive but short-range, strong nuclear force holding it all together.
The strong force has limits.
It acts effectively only over distances of about 1 femtometer. If the nucleus gets too big, parts of it might be too far apart for the strong force to hold them effectively against the repulsion. It's like a giant trying to hold on to something too spread out for its arms to fully wrap around.
Okay, remind us of the main types of decay. Alpha decay first.
Right, alpha decay is common in very heavy nuclei. The nucleus ejects an alpha particle, which, as we know, is essentially a helium nucleus, 2 protons, and 2 neutrons bound together, He4.
So the original nucleus loses 2 protons and 2 neutrons.
Correct. The result of this emission is a new element because the atomic number of protons has decreased by 2 and the mass number has decreased by 4. For example, uranium-238 decays via alpha emission into thorium-234.
Okay, then we have beta decay. That's more complex.
A bit more complex, yes, and it's regulated by the weak nuclear force, another fundamental interaction. There are a couple of main types. In the most common type, beta-minus decay, a neutron inside the nucleus transforms into a proton.
A neutron becomes a proton.
It does. To conserve charge and other quantum numbers, this transformation is accompanied by the emission of an electron, which is called a beta particle in this context, and an electron antineutrino.
So the nucleus gains a proton, loses a neutron.
Exactly. This process increases the atomic number of the nucleus by 1, since there's 1 more proton, but the mass number stays the same. Lost a neutron, gained a proton. This often happens in nuclei that have too many neutrons for stability. For example, carbon-14 decays via beta-minus emission into nitrogen-14.
Okay, and the opposite can happen too.
Yeah.
Proton to neutron.
Yes, that's beta-plus decay, or positron emission. A proton inside the nucleus transforms into a neutron. To conserve charge, it emits a positron, which is the antimatter counterpart of the electron. Same mass, but positive charge, also called a beta particle here, and an electron neutrino.
So atomic number goes down by 1, mass number stays the same.
Correct. This tends to happen in nuclei with too many protons. There's also a related process called electron capture. Instead of emitting a positron, the nucleus captures one of the atom's own inner shell electrons. This electron combines with a proton in the nucleus to form a neutron, and only a neutrino is emitted. The effect on the nucleus is the same as positron emission. Atomic number decreases by 1, but it's often more energetically favorable, especially in heavier atoms.
So alpha changes the element down, beta changes it up or down. What about gamma decay?
Gamma decay is different. It doesn't change the number of protons or neutrons, so it doesn't change the element or isotope. Instead, it results from a change in the energy level of the nucleus itself. Often, after an alpha or beta decay, the resulting daughter nucleus is left in an excited, high-energy state.
Like an electron in an excited orbital, but for the whole nucleus.
Exactly analogous. To return to its lower energy ground state, the nucleus releases the excess energy by emitting a high-energy photon, which we call a gamma ray. So gamma decay usually follows alpha or beta decay as the nucleus settles down.
Okay, those are the main 3. Are there others?
Yes, beyond these common types, there are other rarer forms of radioactive decay. Some very unstable nuclei might eject a single proton or neutron or even larger clusters of nucleons. Some can undergo double beta decay, emitting 2 beta particles simultaneously. There's also internal conversion, where the excited nucleus transfers its energy directly to one of the atom's own electrons, ejecting it at high speed. This electron is not a beta particle, and sometimes high-energy photons that aren't technically gamma rays are also emitted.
And the really big ones can just split apart.
Right. For some very large, heavy nuclei, like californium-252, spontaneous nuclear fission can occur, where the nucleus literally splits into 2 or more smaller fragment nuclei, plus several free neutrons, releasing a tremendous amount of energy.
Wow, a whole zoo of decay modes. What's truly characteristic of all radioactive isotopes, though, is their half-life, right?
Absolutely fundamental. Each specific radioactive isotope has a characteristic fixed decay time period, its half-life. This is defined as the amount of time needed for half of a given sample of that isotope to decay into something else.
So if you start with 100 atoms, after one half-life, you have 50 left.
Exactly. And after a second half-life, you'd have half the remainder, so 25 atoms left. After a third, 12 or 13, and so on. It's an exponential decay process.
And these half-lives vary wildly.
Oh, enormously. They can range from tiny fractions of a second for some highly unstable isotopes to billions of years for isotopes like uranium-238 or thorium-232. This consistent, predictable decay rate is precisely what makes certain radioactive isotopes such powerful tools for dating ancient artifacts, like carbon-14, or geological formations, like uranium-lead dating.
Okay, fascinating stuff. Moving on from decay and stability, atoms also possess intriguing magnetic properties. This comes down to another intrinsic quantum mechanical property called spin, doesn't it?
Yes, exactly. Elementary particles like electrons, protons, and neutrons all possess this intrinsic quantum mechanical property called spin.
Is it like they're actually spinning?
It's analogous to an object spinning around its own axis, generating angular momentum, but it's not literal rotation in the classical sense, especially as these particles are considered point-like or have wave-like properties. It's just an inherent quantum property they possess, like charge or mass. For electrons, protons, and neutrons, their spin quantum number is 12.
Okay, so they have this intrinsic spin. How does that relate to magnetism?
Well, any moving charge or intrinsic spin creates a magnetic field. In an atom, you have a few sources of magnetism. Electrons orbiting the nucleus, in their wave-like way, have orbital angular momentum, which creates a magnetic field. Electrons, protons, and neutrons also have their intrinsic spin, angular momentum, which also creates a magnetic field. And the nucleus itself can have an overall nuclear spin if it has an odd number of protons or neutrons, leading to a nuclear magnetic moment.
So multiple contributions to the atom's overall magnetic character. Which one dominates?
By far, the electron spin is the most dominant contributor to an atom's overall magnetic moment. The nuclear magnetic moment is much, much weaker.
So if electrons have spin and create magnetic fields, why isn't everything magnetic?
Because of pairing and the Pauli exclusion principle again. In atoms or molecules with an even number of electrons, those electrons tend to pair up in orbitals. When they pair up, one electron will have a spin-up state, plus 12, and the other will have a spin-down state, negative 12.
Opposing spins.
Exactly. And their corresponding magnetic moments point in opposite directions and cancel each other out. So atoms or molecules where all electrons are paired up often have a net zero magnetic dipole moment. They are diamagnetic.
Okay, that makes sense. But what about materials that are magnetic, like iron?
Right. In certain elements, particularly the ferromagnetic ones like iron, cobalt, and nickel, their atoms have an odd number of electrons, which leads to unpaired electrons in some of their orbitals. Each of these unpaired electrons has a net spin magnetic moment.
So the atom itself acts like a tiny magnet.
Yes. And in ferromagnetic materials, there's an additional effect called the exchange interaction. The electron orbitals of neighboring atoms overlap in the crystal structure, and a lower energy state is achieved when the spins of these unpaired electrons in adjacent atoms align parallel to each other.
They cooperate to line up?
Exactly. This spontaneous alignment over large domains within the material is what causes ferromagnetic materials to produce a strong, measurable, macroscopic magnetic field to be permanent magnets.
What about paramagnetism?
Paramagnetic materials also have atoms with unpaired electrons and thus net magnetic moments. However, in the absence of an external magnetic field, these atomic moments are randomly oriented due to thermal energy, so the material as a whole isn't magnetic. But when you apply an external magnetic field, the atomic moments tend to align with the field, making the material weakly attracted to the magnet.
Got it. And you mentioned nuclear spin earlier. That is a really important application, doesn't it? MRI?
Absolutely crucial application. As we said, a nucleus will have an overall spin, and thus a tiny magnetic moment, if it has an odd number of protons or an odd number of neutrons, or both. Normally, in a sample of material, these nuclear spins are randomly oriented.
Pointing every which way.
Right. But for certain nuclei, particularly hydrogen nuclei, protons, which are abundant in the water and fat in our bodies, it's possible to use a strong external magnetic field to partially align these nuclear spins. Then radio waves are used to flip these spins, and when the radio waves are turned off, the spins relax back, emitting faint radio signals that can be detected.
And the signals tell you about the tissue.
Yes, the timing and strength of these signals depend on the chemical environment of the protons. By analyzing these signals using complex algorithms and magnetic field gradients, magnetic resonance imaging, MRI, can construct incredibly detailed images of soft tissues inside the human body, providing invaluable diagnostic information non-invasively. It's a direct application of manipulating and detecting the quantum spin of atomic nuclei.
Truly amazing technology derived from fundamental atomic properties. Okay, spin also plays a role in how electrons occupy energy levels and interact with light. Let's talk about the atom's quantum staircase, its energy levels.
Right. So as we discussed with Bohr and Schrödinger, in the quantum mechanical model, a bound electron inside an atom cannot just have any arbitrary amount of energy. It can only occupy a discrete set of allowed energy levels or states, each associated with a specific orbital or set of orbitals.
The quantum staircase.
Exactly. The potential energy of an electron in an atom is considered negative relative to a free electron at rest far away, which is defined as zero energy. The energy becomes more negative, lower, as the electron gets closer to the positively charged nucleus, reflecting the stronger attraction. The lowest possible energy state an electron can occupy is called the ground state.
And anything higher is?
An allowed energy level above the ground state is called an excited state.
And electrons jump between these states by interacting with photons.
Precisely. For an electron to jump from a lower energy state to a higher one, example from the ground state to the first excited state, it must absorb a photon whose energy exactly matches the energy difference between those two levels. AE equal HF, where H is Planck's constant and F is the photon's frequency.
It needs the right energy kick.
Exactly. Conversely, an electron already in an excited state can spontaneously drop down to a lower unoccupied energy level by emitting a photon with an energy equal to that energy difference.
Releasing the excess energy as light.
Right. And these jumps between orbitals happen in that particle-like fashion we mentioned. One photon absorption excites one electron dropping emits one photon.
And because the energy levels are discrete and unique for each element.
The energies, and therefore frequencies or wavelengths, of the photons that can be absorbed or emitted are also discrete and unique. This collection of specific energy values appears as a series of distinct lines or bands in the electromagnetic spectrum. This is the characteristic spectrum, the unique fingerprint or barcode for each chemical element.
Let's revisit absorption and emission spectra quickly, because they're so key to identifying elements.
Sure. Imagine you shine a continuous spectrum of light, like white light containing all visible frequencies, through a cool gas of a particular element. The atoms in the gas will absorb photons only at those specific frequencies that correspond to the energy differences between their electron levels.
So those frequencies get removed from the light passing through.
Exactly. If you then look at the spectrum of the light that has passed through the gas, you'll see dark lines, absorption lines, at those specific frequencies where the photons were absorbed by the atoms, causing electrons to jump up to excited states.
Okay. And emission.
Now imagine you look at that same gas, but maybe it's been heated or electrically excited, so its electrons are already in excited states. As those electrons spontaneously drop back down to lower energy levels, they will emit photons only at those same characteristic frequencies. So if you look at the light coming from this excited gas, without the continuous background source, you will see bright lines, emission lines, against a dark background, precisely at the frequencies corresponding to those electron transitions.
So absorption shows dark lines where light is missing. Emission shows bright lines where light is created.
Perfectly summarized. And spectroscopic measurements of the precise positions, strengths, and even widths of these absorption or emission lines are incredibly powerful tools. They allow us to determine the chemical composition and even physical properties like temperature, pressure, magnetic fields of substances, whether it's a sample in a lab or the atmosphere of a distant star or planet.
And there are even finer details in these spectra. Subtle splittings.
Yes, indeed. Close examination of spectral lines, especially with high-resolution spectrographs, can reveal what's called fine structure splitting. Some lines that look single at low resolution are actually composed of two or more very closely spaced lines. This occurs due to an effect called spin-orbit coupling, which is an interaction between the electron's intrinsic spin magnetic moment and the magnetic field generated by its orbital motion around the nucleus.
Wow, subtle interactions causing visible effects. What about external fields?
External fields also affect the energy levels in spectra. When an atom is placed in an external magnetic field, its spectral lines can split into multiple components. This is known as the Zeeman effect, caused by the magnetic field interacting with the atom's overall magnetic moment, mostly due to electron spin and orbit.
Okay. And electric fields.
An external electric field causes a similar splitting and shifting of spectral lines, known as the Stark effect. Both the Zeeman and Stark effects provide valuable information about the strength of external fields acting on atoms, for example, in plasmas or astrophysical environments.
And this detailed understanding of energy levels and photon interactions is what makes lasers possible, right? It seems like a huge leap from spectra to lasers.
It's actually a direct application of a specific quantum phenomenon related to these transitions called stimulated emission.
Stimulated emission, how does that work?
Normally, an excited electron emits a photon spontaneously when it drops to a lower energy level. But if an electron is already in an excited state, and an incoming photon arrives with precisely the energy corresponding to the transition down to a lower state, that incoming photon can stimulate the excited electron to drop down and emit another photon.
So now you have two photons instead of one.
Yes, and here's the crucial part. The newly emitted photon is an exact clone of the original stimulating photon. It has the same energy, frequency, the same direction of travel, and the same phase. Their wave patterns are perfectly synchronized or coherent.
Identical twins, perfectly in step.
Exactly. So if you can create a situation where you have more atoms in an excited state than in the lower state of population inversion, and you contain these atoms in a cavity with mirrors.
A chain reaction starts.
Precisely. One spontaneously emitted photon can trigger stimulated emission in another atom, producing two coherent photons. These two can trigger 4, then 8, 16, and so on. It's an amplification process. Some of this light leaks out of a partially reflective mirror as a highly concentrated, coherent beam.
And that's a laser. Light amplification by stimulated emission of radiation. It all comes back to those quantized electron jumps.
It all comes back to the quantum mechanics of the atom.
Okay, these energy levels and electron behaviors, especially the outermost ones, directly determine how atoms interact with each other. This leads us finally to their social lives, valence and bonding behavior.
Yes, valency. It's essentially an element's combining power, a measure of how many chemical bonds it tends to form with other atoms.
And this is determined by the valence electrons.
Primarily, yes. The outermost electron shell of an uncombined atom is called the valence shell, and the electrons occupying that shell are the valence electrons. These are the electrons involved in chemical bonding because they are least tightly bound to the nucleus and are most accessible to interact with other atoms.
And the fundamental rule of stability in chemistry, the driving force, is that atoms tend to react in ways that achieve a full, or sometimes empty, outer valence shell, right? Usually like a noble gas configuration.
That's the octet rule, or duet rule for hydrogen and helium. The tendency to achieve 8 or 2 valence electrons, which is a particularly stable configuration. This drive to achieve a stable electron count is what dictates almost all chemical reactions and bonding.
We see this play out in the main types of chemical bonds.
Definitely. In ionic bonds, there is typically a complete transfer of one or more valence electrons from an atom that easily loses them, like a metal, example sodium, to an atom that readily gains them, like a nonmetal, e.g. chlorine. This creates oppositely charged ions, Na+ and Cl, that are then held together by electrostatic attraction. This usually happens between elements on opposite sides of the periodic table.
Okay, transfer for ionic. What about covalent?
In covalent bonds, atoms, typically nonmetals, share pairs of valence electrons rather than transferring them. Each atom contributes one electron to the shared pair, and that pair is attracted to the nuclei of both atoms, holding them together in a molecule. This allows both atoms to effectively count the shared electrons towards achieving their stable octet. Carbon, forming the backbone of organic chemistry, forms 4 covalent bonds. Many elements display multiple valences, meaning they can form different numbers of covalent bonds depending on the situation.
And this inherent bonding behavior dictated by valence electrons is why the periodic table is so incredibly useful and predictive, isn't it?
It's the key to its power. Elements with the same number of valence electrons are placed in the same vertical column or group. And because they have similar valence electron configurations, they exhibit similar chemical properties. That's why group 1 elements, lithium, sodium, potassium, etc., are all reactive alkali metals, and group 17 elements, fluorine, chlorine, bromine, etc., are all reactive halogens.
And the horizontal rows, the periods, track the filling of shells.
Correct. The horizontal rows correspond to the filling of successive principal electron quantum shells, energy levels. As you move across a row, you're adding electrons to the same outer shell.
until you reach the far right, the noble gases.
Like helium, neon, argon, krypton. They have completely filled outer valence shells, 2 electrons for helium, 8 for the others. This is an extremely stable configuration, which is why they are so chemically inert or unreactive under normal conditions. They have little tendency to gain, lose, or share electrons.
Okay, and beyond how individual atoms bond, quantities of atoms also exist together in various bulk forms, depending on the physical conditions. These are the familiar states of matter.
Right, depending on temperature and pressure, large collections of atoms or molecules exist in different phases or states. Solids, where particles are rigidly held in fixed positions. Liquids, where particles can move past each other but remain close. Gases, where particles move randomly and are far apart. And plasmas, a high-energy state where atoms are ionized, consisting of free electrons and ions.
But what's cool is that even within a single state, like solid, a pure element can sometimes exist in different structural forms, right? Allotropes.
Exactly. Allotropes are different structural modifications of the same element in the same physical state. They arise because the atoms can be bonded together or packed in different ways.
Give us some examples.
The classic example is solid carbon. It can exist as soft, black, electrically conductive graphite, where carbon atoms are arranged in flat hexagonal sheets that slide easily over each other. Or it can exist as extremely hard, transparent, insulating diamond, where each carbon atom is strongly bonded to 4 others in a rigid tetrahedral network. Same element, same solid state, vastly different properties due to different atomic arrangements.
Any others?
Gaseous oxygen is another example. It normally exists as dioxygen, O2, the molecule we breathe, but it also has an allotrope called ozone, O3, which has very different chemical properties and plays a crucial role in the upper atmosphere. White phosphorus and red phosphorus are allotropes of solid phosphorus.
Fascinating. And pushing the boundaries to extreme conditions, at temperatures near absolute zero, atoms can form that exotic state of matter you mentioned earlier, the Bose-Einstein condensate.
Yes, the Bose-Einstein condensate, or BEC. This state was predicted by Satchandra Nath Bose and Albert Einstein in the 1920s, but only created experimentally in 1995. It forms at extremely low temperatures, just billionths of a degree above absolute zero.
What happens at those temperatures?
Under these extreme conditions, quantum mechanical effects, which are normally only apparent at the atomic scale, become dominant and observable on a macroscopic scale. If the atoms are bosons, particles with integral spin, unlike fermions like electrons, a large fraction of them can collapse into the lowest possible quantum energy state.
They all occupy the same state. Isn't that forbidden?
It's forbidden for identical fermions by the Pauli exclusion principle, but not for bosons. So in a BEC, this supercooled collection of bosonic atoms essentially loses its individual identity and behaves as a single quantum entity, a single giant matter wave, a superatom, if you will.
Wow. And why is that useful?
BECs provide a unique laboratory for studying fundamental quantum mechanical phenomena directly on a macroscopic scale. They allow scientists to perform fundamental checks of quantum theory and explore bizarre quantum behaviors like superfluidity and interference between separate condensates. It's a window into the quantum world made large.
Incredible. So we've discussed the atom's structure, its properties, how it behaves, how it bonds, and even its exotic states. But the ultimate practical question remains: how do we actually see or identify something so incredibly small? How do we detect the indivisible?
That's been a monumental challenge throughout the history of science, hasn't it? As we established, atoms are thousands of times smaller than the wavelengths of visible light, so conventional optical microscopes simply can't resolve them. They're fundamentally limited by the diffraction of light.
So looking with light is out. What was the breakthrough?
One of the major breakthroughs came with the invention of devices that didn't rely on light, but instead exploited other physical phenomena that occur at the atomic scale. A prime example is the Scanning Tunneling Microscope, or STM, developed in the early 1980s.
STM. And this allows us to actually visualize individual atoms on surfaces.
It does remarkably well on electrically conductive or semiconductive surfaces.
How does it manage to see something that small without using light? What's the trick?
The STM works by harnessing a purely quantum mechanical phenomenon called quantum tunneling.
Tunneling, like electrons digging through barriers.
Sort of. Imagine you have 2 electrodes separated by a very thin insulating barrier, like a vacuum gap, just a nanometer or so wide. Classically, electrons shouldn't be able to cross that gap, but quantum mechanics says there's a non-zero probability that an electron can tunnel through the barrier, appearing on the other side, even if it doesn't have enough energy to classically overcome it.
Okay, weird quantum effect. How does the STM use it?
In an STM, one electrode is the surface you want to image. The other is an incredibly sharp metal tip, ideally tapering down to just a single atom at its very end. A small voltage is applied between the tip and the surface.
So electrons can tunnel between the tip and the surface across the tiny vacuum gap.
Exactly. And here's the key. The magnitude of this tunneling current, the flow of electrons across that gap, is exponentially dependent on the separation distance between the tip and the surface. It's extremely sensitive to tiny changes in distance.
Exponentially. So a tiny change in height makes a big change in current.
A huge change. So as the microscope scans the tip laterally across the surface, a feedback loop constantly adjusts the tip's vertical height, its distance from the surface, to maintain a constant tunneling current.
So it keeps the current steady by moving the tip up and down.
Precisely. The precise vertical movements of the tip, as it follows the contours of the surface to keep that current constant, are recorded. This effectively maps out the surface's topography at the atomic level. What you're really imaging is the local density of electron states, effectively the shape of the electron clouds of the surface atoms.
Giving us a picture of individual atoms lined up on the surface. That's incredible.
It's an incredible feat of engineering and physics, allowing us to directly visualize the atomic world for the first time. However, the STM does have limitations.
Right.
Well, it generally only works well for conductive or semiconducting surfaces where electrons can tunnel easily. It also requires extremely stable conditions, minimal vibration, clean surfaces, ultra-high vacuum often. And while it can visualize atoms, it's not inherently chemically specific. Just by looking at the bumps, you can't always tell what element each atom is.
So you can see them, but not necessarily identify them just with STM. To truly identify an atom, especially its isotope, we often need to weigh it, right, back to mass.
Exactly, and that's where mass spectrometry comes in, a workhorse technique in chemistry and physics.
How does bending something in a magnetic field tell you its mass? Remind us of the principle.
The basic principle is elegant. First, you need to ionize the atoms or molecules in your sample, typically by knocking off an electron to give them a positive charge. Then you accelerate these ions using an electric field so they all have roughly the same kinetic energy.
Okay, charged particles moving fast.
Then you pass this beam of ions through a strong magnetic field. A moving charged particle experiences a force in a magnetic field, the Lorentz force, that is perpendicular to both its velocity and the field direction. This force causes the ion's path to bend into a circular arc.
And the bending depends on mass.
Crucially, yes. The radius of this circular path depends on the ion's mass-to-charge ratio. For ions with the same charge, usually +1, heavier ions have more inertia and will bend less, follow a wider arc, while lighter ions will bend more sharply, follow a tighter arc.
Like trying to turn a truck versus a bicycle at the same speed.
Exactly. So a mass spectrometer uses this principle. It separates the ions based on their Mizad ratio by detecting where they land after passing through the magnetic field, or sometimes by measuring their time of flight. The result is a mass spectrum, which shows the relative abundance of ions at each Mizad value.
So if you have a sample with multiple isotopes of an element, say chlorine-35 and chlorine-37,
the mass spectrometer will show two distinct peaks in the spectrum, one at MELZ equals 35 and one at MELZ equals 37. By measuring the relative heights or areas of these peaks, you can determine the precise isotopic composition, the proportion of each isotope in the sample.
incredibly powerful for analysis. How do you get atoms into the gas phase to ionize them, especially from solids?
There are various techniques. For analyzing liquids or solids, you often need to vaporize the sample first. Techniques like inductively coupled plasma, ICP, use an extremely hot plasma and ionized gas, often argon, to atomize and ionize the sample, which can then be fed into a mass spectrometer, ICP-MS, or analyzed by its light emission, ICP-AES.
Okay. Are there even more precise ways to identify and map atoms? You mentioned one earlier, atom probe.
Yes, atom probe tomography, APT, is a remarkable technique. It offers sub-nanometer resolution in 3 dimensions and, crucially, can chemically identify individual atoms.
How does that work? 3D atomic identification.
It uses a very sharp needle-shaped specimen. A high electric field is applied, strong enough to ionize atoms right at the tip surface and evaporate them one by one. These evaporated ions are then projected onto a position-sensitive detector. By measuring the exact position where each ion hits the detector and, critically, its time of flight from the tip to the detector, which depends on its mass-to-charge ratio, the instrument can reconstruct a 3D map of the original sample atom by atom, identifying the element of each atom.
That's practically science fiction made real. seeing and identifying every single atom in a tiny volume.
It's truly pushing the frontiers of material science.
Beyond mass spec and atom probe, are there other ways to identify atoms, maybe non-destructively on surfaces?
Yes, several electron spectroscopy techniques are very useful. For instance, X-ray photoelectron spectroscopy, XPS, bombards a surface with X-rays. These X-rays knock out core-level electrons from the surface atoms. By measuring the kinetic energy of these ejected photoelectrons, we can determine their original binding energy inside the atom.
And binding energy is unique to each element.
Yes, the binding energies of core electrons are highly characteristic of the element and even its chemical state, how it's bonded. So XPS provides non-destructive elemental and chemical analysis of the top few nanometers of a surface. Auger electron spectroscopy, AES, is another related technique that uses an electron beam to initiate a process resulting in the emission of Auger electrons with element-specific energies.
What about using electron microscopes?
Yes, in transmission electron microscopes, TEMS, which can already resolve atomic structures, you can incorporate techniques like electron energy loss spectroscopy, ELS. This measures how much energy the high-energy electrons of the microscope beam lose as they pass through a thin sample. These energy losses correspond to exciting electrons within the sample atoms, and the pattern of losses is characteristic of the elements present.
So a whole suite of tools using mass, electrons, X-rays. But let's not forget, one of the earliest and maybe most profound ways we identified elements just by looking at light from space.
Absolutely, the spectra of distant stars. As we discussed with emission and absorption lines, the characteristic patterns of light emitted or absorbed by excited atoms act as unique fingerprints.
So we can tell what stars are made of just by analyzing their light.
Exactly. By passing starlight through a spectrograph, astronomers can identify the dark absorption lines corresponding to elements present in the star's cooler outer atmosphere, or bright emission lines from hotter regions or surrounding nebulae. The specific wavelengths of these lines perfectly match the quantized energy level transitions measured for those same elements in labs here on Earth.
It connects the lab to the cosmos. And you mentioned helium earlier, that amazing discovery story.
Yes, it's a classic. In 1868, during a solar eclipse, the French astronomer Pierre Janssen observed a bright yellow spectral line in the sun's chromosphere that didn't correspond to any element known on Earth at the time. The English astronomer Norman Lockyer proposed it was a new element, naming it helium after the Greek word for the sun, helios.
Discovered on the sun before Earth.
That's right. It wasn't until 23 years later, in 1895, that helium was finally isolated and identified chemically here on Earth by William Ramsay. It's a fantastic testament to the power of spectroscopy and the universality of atomic physics.
That's such a cool fact. This incredible ability to detect and identify atoms, from the tiniest sample in a lab using sophisticated machines to the most distant star just by analyzing its light, has allowed us to piece together their grand narrative, their cosmic origin story, and their current state throughout the universe.
Absolutely. When we look at the cosmos on the largest scales, the atoms we know what astronomers call baryonic matter, protons, neutrons, and the electrons associated with them, actually make up only a small fraction of the universe's total energy density.
Only a small fraction. What's the rest?
Current estimates suggest baryonic matter accounts for only about 4 to 5% of the total energy density. About 25-27% is thought to be mysterious dark matter, which interacts gravitationally but not electromagnetically, so we can't see it. And the vast majority, around 70%, is even more mysterious dark energy, which seems to be driving the accelerated expansion of the universe.
So the stuff we're made of, atoms, is actually quite rare, cosmically speaking.
On the grandest scale, yes. And most of this baryonic matter is actually in the form of hydrogen and helium, mostly protons and electrons.
Where is this atomic matter found?
Within galaxies like our own Milky Way, the concentration of baryonic matter is much higher than the cosmic average, of course. The interstellar medium, ISM, the gas and dust between stars, has densities ranging widely from maybe 105 atoms per cubic meter in typical regions up to 109 atoms as in 3 or more in dense molecular clouds where stars form.
What about our own neighborhood?
Our local solar neighborhood is currently in a relatively low-density region called the local bubble, possibly carved out by past supernovae with only about 1,000 atoms per cubic meter on average.
And within the galaxy, where's most of the atomic matter hiding?
The vast majority, perhaps up to 95% of the Milky Way's baryonic matter is actually locked up inside stars.
But you said earlier, inside stars, it's mostly plasma, not neutral atoms.
That's right. Due to the immense temperatures and pressures at the core and throughout much of the volume of a star, the atoms are fully ionized. They exist as a plasma. a soup of bare atomic nuclei, mostly protons and helium nuclei, and free electrons, completely separated and zipping around at high speeds. So atoms in the neutral sense are rare inside stars.
Okay, so where did all these atoms, mainly hydrogen and helium, come from in the first place? The Big Bang.
The very origin of these atoms is a cosmic tale that starts right back at the beginning, with the Big Bang about 13.8 billion years ago. Electrons are thought to have existed very early on, along with quarks, which quickly combined to form protons and neutrons as the universe cooled slightly.
And then the first nuclei formed.
Yes, within the first few minutes, roughly between 3 and 20 minutes after the Big Bang, the universe was hot and dense enough for nuclear fusion to occur. This period is called Big Bang nucleosynthesis, BBN. During BBN, protons and neutrons fuse to form most of the universe's light nuclei, primarily hydrogen, just protons, deuterium, 1 proton, 1 neutron, helium-3 and helium-4, and trace amounts of lithium-7 and maybe tiny bits of beryllium and boron.
So the Big Bang made hydrogen and helium, mostly.
Overwhelmingly, yes. About 75% hydrogen and 25% helium by mass, with just tiny fractions of the others.
But the universe at this point was still a hot, opaque plasma, right? Nuclei and electrons flying around separately.
Correct. For the next few 100,000 years, the universe was still too hot and energetic. Any electron that tried to bind with a nucleus would quickly be knocked off again by a high-energy photon. The universe was opaque because these photons were constantly scattering off the free electrons.
So when did neutral atoms finally form?
That happened around 380,000 years after the Big Bang, during an era called recombination. As the universe continued to expand and cool, the average energy dropped below the ionization potential of hydrogen and helium. At this point, it became energetically favorable for electrons to be captured by nuclei and remain bound, forming stable neutral atoms.
The universe became neutral.
Largely neutral, yes. And this had a profound consequence. Without abundant free electrons to scatter them, photons could now travel freely through space. The universe became transparent to light for the first time. The fossil light from this very epoch is what we observe today as the cosmic microwave background radiation, CMB.
Wow. Okay, so the Big Bang made hydrogen and helium, but it produced essentially no carbon or heavier elements, right? So where did all the elements that make up planets, and indeed us, come from?
That's the crucial role of stars. Stars are the universe's element factories, responsible for creating nearly all elements heavier than helium through stellar nuclear synthesis.
How do they do that? Fusion again.
Primarily through nuclear fusion in their incredibly hot and dense cores. Stars spend most of their lives fusing hydrogen to more helium, like our sun does. In more massive stars, or later in the lives of stars like our sun, when hydrogen runs low in the core, they can start fusing helium into heavier elements.
Like carbon.
Yes. The key step is the triple alpha process, where 3 helium nuclei, alpha particles, fuse together to form a carbon nucleus, carbon-12. From carbon, further fusion reactions, capturing more helium nuclei or fusing with other light elements, can build up elements like oxygen, neon, magnesium, silicon, all the way up to iron and nickel in the cores of the most massive stars.
So stars forge elements up to iron through fusion. What about things like lithium, beryllium, boron? They were made in the Big Bang only in tiny amounts.
Right, BBN made very little of them. Most of the lithium, especially lithium-6, beryllium, and boron we see today, are thought to be generated primarily through a different process called cosmic ray spallation.
Spallation, what's that?
This happens out in interstellar space. High-energy cosmic rays, which are mostly fast-moving protons and atomic nuclei accelerated by things like supernovae, slam into heavier atomic nuclei like carbon or oxygen in the interstellar gas or dust. This high-energy collision can shatter the target nucleus, spalling off fragments, including isotopes like lithium, beryllium, and boron.
So cosmic rays break down heavier elements into these lighter ones, okay? But what about all the elements heavier than iron? Fusion stops there. Where do gold, lead, uranium come from?
Those require even more extreme conditions than the cores of normal stars during their stable lifetimes. Elements heavier than iron are produced primarily in catastrophic cosmic events through processes involving neutron capture.
Neutron capture, adding neutrons to existing nuclei.
Exactly. There are 2 main processes. The S process, slow neutron capture, occurs relatively slowly inside certain types of evolved giant stars called asymptotic giant branch, AGB stars. Neutrons are captured one by existing heavy nuclei, like iron. If the resulting nucleus is unstable, it usually has time to undergo beta decay, neutron to proton, increasing the atomic number before another neutron is captured. This process builds up elements gradually along the valley of beta stability, producing many isotopes up to lead and bismuth.
Okay, that's the slow process. What's the fast one?
The RAP process, rapid neutron capture, requires an incredibly high density of neutrons, so that nuclei capture many neutrons very quickly before they have a chance to beta decay. This allows the process to bypass unstable regions and build up very heavy neutron-rich nuclei far from stability. These neutron-rich nuclei then subsequently beta decay back towards stability, producing the heaviest elements, including things like gold, platinum, uranium, and plutonium.
And where do these incredibly neutron-rich conditions occur?
The exact sites are still debated, but the leading candidates are core collapse, supernovae, the explosions of massive stars, and, perhaps even more importantly, the merger of two neutron stars. The detection of gravitational waves and electromagnetic radiation from a neutron star merger in 2017 provided strong evidence that these mergers are a major source of our process elements.
So stars live, stars die, stars collide, and in doing so, they forge all the elements beyond hydrogen and helium, scattering them into space to form the next generation of stars, planets, and people.
That's the cosmic cycle of matter, exactly. We are stardust, as Carl Sagan famously said.
So, if the cosmos is the ultimate atom factory, how did our specific planet, Earth, get its atoms?
The vast majority of the atoms that make up our planet, the sun, and everything else in the solar system were present in the enormous cloud of gas and dust, the solar nebula that collapsed under gravity about 4.6 billion years ago to form our solar system. This nebula was itself enriched with heavier elements forged in previous generations of stars that lived and died in our galaxy.
So we inherited our atoms from long-dead stars.
Mostly, yes. However, a small fraction of the atoms on Earth today were not part of that original inheritance. They are the products of radioactive decay that has happened since the Earth formed.
And their proportions help us date the Earth.
Precisely. By measuring the ratios of certain long-lived radioactive parent isotopes, like uranium-238 or potassium-40, to their stable daughter isotopes, like lead-206 or argon-40, in rocks and minerals, scientists can determine how long those rocks have been solidifying, giving us the age of the Earth about 4.54 billion years. Much of the helium found trapped in Earth's crust, for example, is helium-4 produced from the alpha decay of uranium and thorium over billions of years.
And some atoms are still being made on Earth today.
Yes, as we mentioned, some short-lived radioactive isotopes are continuously generated by natural processes. Carbon-14 is the prime example, constantly produced by cosmic rays hitting nitrogen atoms in the upper atmosphere. Tritium, hydrogen-3, is also produced this way in small amounts.
And then there are the ones humans make.
Right. Some atoms, or rather isotopes, found on Earth today are artificially generated by humans, either deliberately in nuclear reactors, like plutonium-239 for power or weapons, or particle accelerators, or as byproducts of nuclear weapons testing in the mid-20th century.
You also mentioned transuranic elements earlier, heavier than uranium. Only plutonium and neptunium occur naturally.
Yes, in incredibly trace amounts. Elements heavier than uranium, atomic number 92, are called transuranic elements. Most of them have relatively short half-lives compared to the age of the Earth. So any primordial transuranics that might have been present when Earth formed would have long since decayed away. However, tiny quantities of neptunium-237 and plutonium-239 are found naturally occurring in uranium ores.
How are they made there?
They are produced continuously through neutron capture by uranium nuclei. Neutrons are present from spontaneous fission of uranium and other reactions, followed by beta decays. But all other transuranic elements like americium, curium, etc., found on Earth are purely artificial.
Okay. And just for scale, how many atoms are estimated to be in the Earth?
The numbers are astronomical, as you'd expect. The Earth contains approximately 1.33 down 150 atoms. That's 133 followed by 48 zeros.
Wow. And how are these atoms arranged here on Earth? Are they mostly individual atoms?
Very few exist as independent atoms. The noble gases in the atmosphere, argon, neon, helium, etc., do exist as individual unbound atoms because they are so unreactive. But that's a tiny fraction.
So most are bonded together?
Overwhelmingly, yes. About 99% of our atmosphere, for instance, consists of atoms bound together in molecules, primarily diatomic nitrogen, N2, and oxygen, O2, plus carbon dioxide, CO2, water vapor, H2O, etc.
And on the surface, in the crust.
The vast majority of atoms at Earth's surface are chemically bonded together to form compounds. Think of water, H2O, salts like NaCl, silicates making up most rocks based on silicon and oxygen, oxides like iron oxide rust, carbonates, and so on.
And they also form larger structures beyond simple molecules.
Yes, atoms also combine into extended network structures that don't consist of discrete molecules. Examples include crystals like salt or diamond with a repeating lattice structure, liquid and solid metals where valence electrons are delocalized in a sea surrounding positive ions, and glasses, which are amorphous solids lacking long-range order.
So a huge diversity of arrangements for these fundamental building blocks.
Yeah.
Okay, we've charted the atom's history, structure, properties, and its cosmic journey to Earth. But what about the atoms that are truly exotic, pushing the boundaries, or even just theoretical? This is the frontier of atomic and nuclear physics.
Indeed, we're talking about things like super heavy elements. As we know, all nuclides with atomic numbers higher than 82, lead, are radioactive. And generally, as elements get heavier and heavier, their nuclei become more unstable, and their half-lives tend to get shorter and shorter.
Why is that? More proton repulsion.
Exactly. The increasing electrostatic repulsion between the large number of protons makes the nucleus prone to spontaneously fissioning, splitting apart. This trend suggested for a long time that there might be a practical limit to how heavy an element could possibly exist, even fleetingly.
But then came the idea of the island of stability. What's that?
Based on nuclear shell models, remember the magic numbers conferring extra stability. Theorists predicted in the 1960s that there might be a region, an island, of relatively long-lived isotopes for super heavy elements centered around predicted nuclear magic numbers for both protons, like Z114, and neutrons, like N184.
So super heavy elements that might live longer than expected.
Potentially much longer. Instead of decaying in microseconds or less, isotopes on this predicted island of stability might have half-lives ranging from minutes to days, maybe even thousands or millions of years in some optimistic predictions.
Has this island been reached? Have we found these long-lived super heavies?
It's an active and incredibly challenging area of experimental research. Scientists in labs in Russia, Germany, the US, and Japan have succeeded in synthesizing elements up to 118 oganesson by bombarding heavy target nuclei with beams of other heavy ions. Some of the isotopes created for elements around 110, 114 do seem to have slightly longer half-lives than their neighbors, offering hints that we might be approaching the shores of this island. But confirming truly long-lived isotopes remains a huge experimental hurdle. It's like searching for a hidden treasure map for fundamentally new forms of matter.
A very exciting frontier. Beyond super heavy elements, there's also the whole realm of exotic matter, starting with antimatter.
Right. As predicted by Paul Dirac in the late 1920s and later confirmed experimentally, every fundamental particle of matter has a corresponding antiparticle. Antiparticles have the exact same mass as their matter counterparts, but opposite values for other properties, most notably electric charge.
So the electron's antiparticle is the positron, positive charge.
Correct. The proton's antiparticle is the antiproton, negative charge. The neutron's antiparticle is the antineutron, also neutral, but with opposite quark content and magnetic moment direction.
And what happens when matter meets antimatter?
Annihilation. When a particle and its corresponding antiparticle meet, they annihilate each other completely, converting their entire combined mass into energy, typically in the form of high-energy photons, gamma rays, or other particle-antiparticle pairs, according to EMC2.
The ultimate energy release. But the big mystery here is, why is there so little antimatter around?
That is one of the biggest unsolved problems in physics and cosmology. The Standard Model predicts matter, and antimatter should have been created in almost equal amounts in the Big Bang. If that were strictly true, they should have all annihilated each other very early on, leaving a universe filled only with radiation and no matter left to form stars, galaxies, or us.
But clearly, matter won.
Yes, our universe has a massive imbalance, overwhelmingly favoring matter over antimatter. There must have been some subtle difference in the laws of physics governing matter and antimatter in the very early universe, a violation of CP symmetry, that led to a tiny excess of matter surviving the initial annihilation phase. We don't fully understand the mechanism, though theories collectively known as baryogenesis attempt to explain it.
So as a result, no antimatter atoms have ever been discovered naturally in the universe.
None have been convincingly detected, despite searches. It seems the universe we see is made entirely of matter.
But we can make antimatter in labs.
Yes. Antiparticles like positrons and antiprotons are routinely created in high-energy particle collisions in accelerators like those at CERN or Fermilab. And in 1995-1996, a monumental achievement occurred at CERN. Scientists managed to combine positrons and antiprotons to synthesize the first complete antimatter atom, the antimatter counterpart of the hydrogen atom, called antihydrogen.
Making anti-atoms, that's incredible. Why is that important?
It allows scientists to perform precise experiments to test fundamental symmetries between matter and antimatter. For example, do antihydrogen atoms have exactly the same energy levels and spectral lines as hydrogen atoms? The CPT theorem, a cornerstone of quantum field theory, predicts they should be identical. Testing this with high precision is a crucial check of our fundamental understanding.
Okay, and beyond antimatter atoms, are there other kinds of exotic atoms?
Yes, other types of exotic atoms can be created, usually very briefly, by replacing one of the standard components, proton, neutron, or electron, with another particle that has the same charge but different properties, like mass or lifetime.
Such as?
For example, if you replace the electron in an atom with a muon, which is like a heavier cousin of the electron, about 200 times heavier, but still negatively charged, you create a muonic atom. Because the muon is heavier, its orbit is much closer to the nucleus, making mnemonic atoms sensitive probes of nuclear size and structure. You can also have pionic atoms with a pion replacing an electron, kaonic atoms, or even protonium, a bound state of a proton and an antiproton.
Why do these exotic atoms matter? It sounds like very specialized, short-lived stuff.
They are indeed often short-lived and hard to create, but they are incredibly valuable tools for testing the fundamental predictions of physics, particularly the Standard Model and quantum electrodynamics, QED, under extreme conditions. By precisely measuring the properties of these exotic atoms, like their energy levels, scientists can search for tiny deviations from theoretical predictions that might hint at new physics beyond the Standard Model, potentially uncovering new particles, forces, or dimensions. They are precision probes of the fundamental laws of nature.
So we've truly traveled from the ancient Greek philosophers pondering the uncuttable, through centuries of discovery, to the cutting edge of particle physics where we synthesize the anti-atoms and search for mythical islands of stability among the super heavy elements. It's an absolutely incredible journey of human understanding.
And what a journey it's been. We started, didn't we, with the atom as maybe a simple, indivisible sphere, and we've ended up with this complex, probabilistic cloud of quarks and leptons, all governed by the strange and beautiful rules of quantum mechanics.
It really underscores how these tiny particles, these atoms, are truly the fundamental building blocks of all the matter we see and experience. They govern everything from the light emitted by a distant star to the intricate biochemistry happening inside your own body right now.
And understanding the atom isn't just some abstract academic exercise, is it? It underpins virtually all of modern science and technology. Chemistry, materials science, molecular biology, geology, nuclear energy, medical imaging like MRI and PET scans, all of it rests on our knowledge of the atom.
It's the invisible foundation, really, of everything we perceive and interact with.
So, thinking about how far we've come, considering how our understanding of the atom has evolved so dramatically, from that philosophical guess to this intricate, probabilistic quantum reality, what might the next century reveal about the atomic realm that we can't even begin to imagine today?
That's a great question. And maybe something more personal for you, the listener, to ponder. You are made of these incredible tiny structures, these atoms, which are themselves mostly empty space, animated by quantum rules. What does that surprising, counterintuitive fact tell you about the nature of your own existence, but a substance of reality itself?
Definitely a thought to truly deep dive into.